Hi there, Ryan. How are you doing?
Hello. How's it going?
It's going well.
Yeah.
All right, we're going to hand it over to Ryan for his talk. Thank you very much.
Thanks. Hey there, everyone. My name's Ryan. I am an embedded engineering consultant, contractor, whatever you want to call me. I've been working in the embedded world for the last probably 5 years now. I've developed in a whole variety of languages, all the whole stack, C, C++, recently been getting into Rust. I tend to work in the safety critical, timing critical kind of realm. Big project I'm on right now, we've been doing an embedded device, obviously embedded medical device, implantable class 3 medical device for patients to help cure sleep apnea. And I recently got in contact with Rtic, which is a company up in Berlin after the Oxidize 1K conference earlier this year, about doing some firmware development in Rust for some of their hardware. And so I kind of wanted to give a different take on the talk here, where instead of going into some of the internals in Rust, I wanted to talk about a project that we did with it and kind of the experience in working with the cargo ecosystem and all the various different crates that we have. And so Rtic develops open source, typically hardware and firmware solutions for use in quantum physics research labs. And so they have a new project that they have called Stabilizer that is used for stabilizing laser frequencies. And essentially the board shown on the right here boils down to 2 analog inputs that we want to sample really quickly. We pass the data through a digital filter, and then we can reconstruct the data on the output, pass the digital codes back out to a DAC, and we can reconstruct a new waveform. And then we can use this as a feedback loop to control the laser frequencies because they need to have them really precise when they're performing quantum physics experiments. And so Rtic had just developed some new hardware for this stabilizer going from v1.0 to v1.1. They swapped around a lot of the pins. They had an existing firmware solution that was working on the v1.0 hardware, but what they were looking for is converting all of that to using some of the STM HALs that are out there because it was originally developed using only the peripheral access crate. And so one of the other major portions of this project was that there is a mezzanine card that they wanted to place on top of Stabilizer that is essentially just another form. It implements another algorithm for stabilizing lasers using the pound-driver-Hall technique. And if that's all you know about quantum physics, don't worry. The only parts of that algorithm I actually understand are on Wikipedia. If you're looking for more in-depth quantum physics here, I'm sorry, you're probably not going to get it in this presentation. My quantum physics is also pretty rusty. So this card that sits on top of Stabilizer is intended to be another, like I said, laser stabilization source. And it doesn't have any microcontroller directly, so it's intended to be controlled by Stabilizer directly. And so essentially what it boils down to is one really interesting high-performance chip that's sitting on there called a direct digital synthesizer. And that chip is capable of generating 4 analog outputs with a known phase relation, amplitude, frequency, and all of that good stuff. And so having that precise control over these waveforms allows the physics experiments or the control algorithms to precisely tune the laser frequencies. And so this card also has a number of various other peripherals on it, such as digital attenuators that we can control to adjust the power inputs for the various RF signals that we're taking in or generating. There's a lot of analog hardware for mixing the various signals together to generate outputs for controlling the laser. But generally, it sits on top of the Stabilizer card, and we talk to the direct digital synthesizer chip over a quad SPI interface, which is essentially just a SPI interface with 4 I/O lines instead of 1. So it allows us to talk really quickly to it. Going back a little bit, Stabilizer, the main control interface that it's used for configuring experiments and such is through an Ethernet interface. And so what Rtic was interested in is allowing all of the various parameters of the DDS chip to be configured through the Ethernet interface, while also providing telemetry and information from the actual Stabilizer platform. And so going forward and looking into how we want to develop this, because there was an existing peripheral access crate implementation that it had the functionality necessary. It was able to talk to the various ADCs, send information out to the DACs. did everything we needed to do. It had the timing, so there's a general structure of the algorithm that we were looking for. It had used RTFM as well. And so we were really looking into how we can leverage as many of the Rust crates in the Rust ecosystem to implementing this application. And so RTIC, formerly known as RTFM, if you watched any of the previous talks, this is going to kind of build on top of that, going into the application layer of some of these crates, is a really nice kind of framework for implementing this kind of application. Because if you think about it, Stabilizer essentially only has three really large tasks that we're trying to do. There's taking in and filtering channel 1, taking in and filtering channel 2, and then handling all of the Ethernet traffic and handling the control interface, sending any log messages out that we need to. But it's also a little bit more complicated because we need to share some of that state between these various tasks. And if we're having some kind of concurrent where the filters are running dynamically in higher interrupt priorities, sharing that state can get complicated and risky. And so RTIC posed a really nice solution for kind of working with this, because we can lock the digital filter states as we're trying to read them so we can send them out of the Ethernet interface, or if the user wanted to update their filter to change what it was doing to the output signals, we can allow them to do that as well. We are also really interested in converting over all of the existing code to using the STM32H7 HAL, largely because this is a fairly new chip, and I don't know if the HAL actually existed before the first implementation of Stabilizer was developed. And so we really wanted to look into using a HAL because it's really nice for expressing exactly what's happening with the system. For example, when you're configuring the whole clock interface for the chip, you can say system clock is running at 200 megahertz. This peripheral clock that is powering the SPI is running at 50 megahertz. And we can really precisely control all of that information and really nicely display it in the source code so that when we're auditing it later to verify functionality, it's explicitly clear what's happening. We also wanted to use the HAL, obviously, for the peripheral implementations. We needed an I2C bus that's going on to a GPIO expander that's sitting on top of the Pounder hardware so that we can control some of the IOs going into the synthesis chip. We also needed to have SPI going to the ADCs and the DACs on the Stabilizer hardware. We needed SPI also going to the digital attenuators that are connected on the Pounder hardware. And so there's all of these various hardware interfaces that we needed to implement, and the HAL had ready-to-go implementations for them. The one thing that we did need that the HAL did not have was that we needed the quad SPI interface to be able to talk to the DDS really quickly. And so we knew going into this that was likely something we were going to have to implement ourselves. There's also an STM32H7 Ethernet crate that explicitly takes in the Ethernet peripherals from the peripheral access crate for the H7 chip and exposes a small TCP PHY device interface, which is a fancy way of saying it allows us to instantiate a TCP stack without having to actually write any code, which is extremely powerful. And so next, I kind of want to get into a little bit more of exactly how we accomplished this, because we finished up the project probably about a month ago. So we were able to leverage small TCP, creating a network stack that sat on top of that STM32H7 Ethernet crate. And if it sounds simple, that's because it is. It was extremely straightforward to get set up and working. Just configuring the GPIO pins to the correct alternate functions, passing in the various peripherals to the STM32H7 Ethernet HAL, creating that interface, providing that interface into the constructor to small TCP, and it basically all worked. It was really impressive. Then we could focus on just implementing. Now we have a TCP port that we can open up, bind to. We implemented a server sitting on top of that uses Rtic and just passes JSON back and forth so that we can have the user send in a request that says like, hey, can you modify the channel 1 output frequency from 500 megahertz to 400 megahertz? And then we can pass that all the way up the stack to go to actually configuring the DDS chip itself. What was really interesting was working on the Stabilizer firmware, because this is the 2-channel chip that is, or a 2-channel board that is sampling the RF inputs, filtering them, and sending them out. Largely because this needed to be really high performance design. We had strict timing requirements. We needed to be able to sample the signals as quickly as we could, filter them, and send them back out. We needed to try and have fixed delay between the input and the output so that the signals were coherent with each other. And so really, if you start thinking about it, well, okay, we need to have a timer periodically. We need to sample them, we need to filter them, and then we need to write them out. So if we set up a timer every 500 kilohertz, then we get our interrupt, we sample the ADCs, we pass it through our digital filter, and we write it back out, right? Like we just do that for the first channel, then we do it for the second channel. Well, it turns out that if we're looking for a really fast implementation, that doesn't quite work. Largely because just the SPI transactions of reading from the ADC and writing to the DAC, if we incorporate those results in too long of a latency, the maximum frequency we're able to run the filter at is about 100 kilohertz or so. And we're trying to get into the range of about 500 kilohertz was the target. And so we're already about 5 times too slow for what we need. And so instead, what we were thinking, okay, well, maybe we can pipeline this implementation as well. And so we set up a timer to, instead of performing an interrupt, it generates a DMA request. And that DMA request writes directly into the peripheral block to start the ADC transaction. Then as soon as the ADC transaction is finished, then we can wake up. We get an interrupt that says, hey, your data is ready. We pass that data into the filter. And then we take the result of the filter, write it out to the DAC. We don't even wait for the SPI transaction of the DAC to finish, and then we continue onward. It's a really nice solution because essentially this boils down to just the blue portions. The digital filter of this is the only foreground task that is being done in this whole pipeline. The entire ADC read, the conversion, writing out to the DACs is all performed automatically in hardware based on DMA requests and timers. And so there's no requirement for any kind of processing in Rtic. And so we can really pipeline all of the implementation and get it running fast. And we were able to hit our 500 kilohertz just fine using this implementation. In fact, we could probably even get it going faster if we needed to, if we can optimize the digital filtering portion of this, as that's kind of the bottleneck at this point. We also got a custom quad SPI interface going using the STM32 HAL. It's kind of an interesting peripheral because there's many ways you can use it. The intended way typically is to map directly some external flash memory or RAM into your chip memory space so that you can use it as extra memory, or you can use it in an indirect way, just kind of like a SPI peripheral where you just do register writes, register reads, and such to various other portions of whatever chip you have on the other end. We also have a driver crate going now for our 809959, which is the DDS chip that generates all of the sinusoidal outputs. We're able to read back any of the frequencies, phases, amplitudes, configure the clock for the DDS chip and all of that. And so now I kind of wanted to get into more like, what did we learn from this whole experience? One, embedded Rust is extremely effective when you're trying to do really high performance time and critical applications, which was a bit surprising to me coming from a C++ background where you've dug into some of the disassembly listings of your previous application. So you know exactly what the compiler is generating. In Rust, it's a bit less transparent because it's a bit more of a new language for me. And so really being able to hit those timer requirements we needed, being able to analyze it with logic analyzers and visualizing the output and saying like, oh yes, we're hitting our 500 kilohertz. We can see exactly where we're spending time. It was really fascinating to see. One thing that was interesting to me is that we had a lot of difficulty with the HAL. And I think this was largely because the HAL was new, and we have managed to work through the fixes by working with the creator, which Richard Meadows, if you're watching this, thank you very much. That is a fantastic HAL. I believe he gave a presentation earlier. But what I mean is with the STM32 HALs, typically the peripheral has to be enabled before you can start working with it so that it allows essentially a clock to go to the portion of the silicon that you're actually working with. And the quad SPI did not have any implementation yet because it's a relatively young HAL. And so there's a lot that still needs to be done. And it's a very complex chip. And the data sheet is probably about 2,000 pages long. It's a little brutal. And so trying to implement a custom quad SPI interface wasn't actually possible with the existing HAL because the peripheral enables were all hidden within the HAL crate. And so using any of the SPI or I2C interfaces didn't allow us to implement our own custom quad SPI interface. So what I'm trying to say is when we're trying to architect our HALs, let's try and make them as versatile as we can for when people are trying to implement their own custom implementations as well, while working within the HAL framework. However, what we did find is that HALs are extremely versatile in when we're trying to make really custom high performance behavior. For example, the ADCs that we have on the stabilizer front end require when the chip select goes low, you need to wait 220 nanoseconds before you start clocking out any of the data because it needs to convert that. And we were able to essentially allow the HAL for the SPI to take in a custom configuration structure that specified all of these hardware level configurations so that even though we weren't having any software intervention for these kind of transactions, so there's no timer wait for this 220 nanoseconds to elapse before we do the transfer, we passed all of that configuration into the SPI constructor in the HAL, and it automatically was able to configure the peripheral to operate in that way. And so we were able to pass these really hardware-dependent configurations through this agnostic driver interface, and it was really impressive to see. We also discovered that interface programming in the embedded HAL allows us to rapidly develop things in the sense where we can develop the DDS chip driver without having any hardware. We can just go ahead and start thinking logically, reading through the datasheet, implementing things and compiling it and checking all of that. And that really allows us power while we're working with our schedules. And that's kind of what I wanted to get into in the next portion as well, is that what was truly impressive to me is how much of this we were able to accomplish using pre-built blocks from Rust and from Cargo, because we were able to leverage Rtic for building all of our task and resource management in the application. We were able to use the HAL for doing a vast majority of all of our peripheral configuration and development. The largest amount of time I spent working at the hardware level was developing the quad SPI interface. We were able to essentially just drop in an entire TCP IP stack using small TCP in probably not even more than about 2 to 3 hours before I was talking to it from my Linux computer. And then we were able to use a number of pre-built device driver crates, such as the GPIO expander on the Pounder hardware. And so really what this gets into is that it is truly absurd to me how quickly we can develop applications when we can leverage the Cargo ecosystem. And so really what I want to try and point out here is that as a result of that, we should really try and pay it forward. So taking our custom driver crates, 89959 DDS chip, even if maybe likely no one else is going to be using that. It's a very complex chip, kind of a niche market in quantum physics, but maybe we can still publish those and put them out into Cargo, because that helps develop the ecosystem. And when we introduce more driver chips, then we obviously get more interest in the language. And when there's more interest, more people are writing drivers. Suddenly we reap the benefits of that, even if we're our own private company, because other people are now providing drivers that we can leverage in our products as well. Other ways we can help pay it back through these projects, implementing bug fixes and HALs. We worked closely with a lot of the guys over at the STMH7 HAL to implement changes into the API and such so that things just work smoother. We can provide usage examples, and we can help improve various interfaces and how the HALs are interacting with our code. And all of that is to help kind of drive the ecosystem forward and help with adoption. And I just want to really stress how incredible it was for me working with this project, because we got a high-speed, timing-critical application with a networking interface going in less than 100 hours. That's less than 2.5 weeks to get a fully functional prototype going for our client. Now, I truly think you're doing a disservice to any of your development if you're not looking into Rust as a potential source for embedded development. And that's coming from an environment of using C, assembly, and C++ as well, because just the amount I was able to get done in this short amount of time was truly absurd. If you look at this, this is a tracking of the time I spent on this project. And the first portion here in April was before we had any hardware available. This was all just software development from a high-level perspective. We took a break in May while we were waiting for the hardware to come in. And then over the next 2 weeks, once we had hardware, we did all the testing and got it up working. And it was truly an impressive experience. So I guess what I really want to say is embedded Rust is definitely production ready. And I think a lot of people are missing out by not taking the chance to look at it. There's a lot of libraries you can leverage. And even if the libraries aren't fully functional yet, it's still more than what you would have otherwise. Because all of this HAL development, when you're doing your own implementation, is something you would have to do anyways. It's something in a C project where you assume that's going to be the first few months of development. You're just going to get the I2C implementation of the SPI going. And so really, even if it's still preliminary or it's hobbyist level or enthusiast, it's still more than what you have now. And that's a really valuable place to come from. So going forward, this project, we really want to replace our TCP server that's sitting on top of the stack because it's kind of this custom SERD JSON that doesn't really make sense because it's only request response oriented. We want to replace that with an MQTT interface, which is, if you don't know what MQTT is, it's kind of an IoT protocol where essentially you can broadcast to some broker. The broker will then facilitate message passing to various clients. And so there's nice applications on Linux that you just run a broker and your whatever you want can connect to it, your little IoT node, and transmit temperature data or any kind of telemetry. And then you can hook up a client on your laptop and it'll plot all of the data in real time. And so there's also brokers that'll hook up to web-based interfaces so that you can store all of this data up into the cloud. And so what we want to do is try and move a lot of the telemetry that Stabilizer and Pounder generate and broadcast that over MQTT instead. We also want to work on getting a lot of our HAL implementations back into the actual HAL. We have the QSPI sitting as a draft PR. We've got custom SPI configurations that we're working on getting the PR in still. There's a number of DMA implementations that we did a little bit hacky, but work. And so we're looking at how we can try and incorporate that back in. So as a last thing, I just wanted to have a shameless plug here for Rtic. Rtic is currently looking for an engineer to help them with some of this embedded Rust development in quantum computing. So if you are interested in looking for a job, please get in contact with me and I will get you in contact with Rtic. Thank you very much. I appreciate all of you listening. I think that is all I have for now.
All right, great. Thank you so much for the presentation. We have a couple of questions ready to go and a lot of people excited about embedded Rust being ready. So I'll start with the first question was, did you use Rtic for all of the timing functions you mentioned in the project?
Yeah, Rtic was basically the whole framework that we were using for the whole thing. All of the timing for like ADCs and stuff was all done at a hardware level. We didn't use. So in terms of scheduling the filters to execute, that was all done using a hardware peripheral timer. So it wasn't using any of the cycle counter or monotonic of Rtic or anything like that.
Great. Our next question is regarding extendable HALs. This is a super good point. Did you add a solution for that in the H7 HAL, or do you have any ideas for how to do it in a neat way? We have someone who would love to do something similar with the F1.
Yeah, so I did not implement the solution, but Richard Meadows did. What he got going is a really nice solution, and it's called the PREC structure, and I don't know exactly what it stands for, but essentially it's an interface that abstracts the STM32 RCC into a programmable reset and control interface. So essentially it exposes a public API for resetting a peripheral or enabling a peripheral. So take a look at the H7 HAL for the PREC structure, and that's a great implementation.
Great. The next question is, would you want to change anything in the ecosystem with your project if you were starting over? Or change anything in the ecosystem or with your project if you were starting over?
If I was starting over, I would not have gone for a custom TCP server implementation. I would have rather gone with an MQTT kind of implementation. There are some still heavily in development MQTT implementations that we were looking at, but it was a little too early initially. So Rtic has a prototype MQTT implementation going, and I've had it running on a Nucleo board and reporting up a little temperature sensor lately. So we're working on stabilizing that as well.
Great. We have someone asking how to contact you. That might be better to drop into the chat. Someone's still typing, so sorry, go ahead.
I'll hop into Matrix after this.